Hello everybody, this is Dr. Christopher White, and in this presentation we're going to continue looking at sedimentary environments and sedimentary rocks. So in this video we're going to look at how do we actually study sedimentary sequences, and this is going to correspond to section 7.13 of your textbook. So as a geologist, you're going to go to an area, you're going to find an outcrop, and you're going to see a sequence of sedimentary rocks in front of you. And it's your job to try and work out the history of that area using the sedimentary rocks that are available. So what are some of the features that a geologist is going to look at when trying to analyse these sedimentary rocks to work out how each layer formed? Well, the first thing a geologist is going to look at is the colour of the layer or layers of rock that you're looking at. Now, a lot of the time, the colour of the layer of rock is not actually that helpful to a geologist. There's lots of different types of rock that have a kind of tan colour to them. There's lots of different types of rock that have a dark grey colour to them. There's lots of different rock types that have a white colour. So those colours aren't going to be particularly helpful. However, there are some colours which have a more limited occurrence. So if we look at this image that we can see here, we can see we have a sequence of rocks that have a rather distinctive rusty red colour to them. So this is going to tell us a couple of things. The first thing it's going to tell us is that obviously this rusty red colour is the result of oxidation. So we know that when this sediment was being liquefied, there was clearly some oxygen around. The other thing it tells us is that this sediment is likely to have formed in an arid or semi-arid environment, desert conditions. And so when we see desert rocks, it's not uncommon for them to develop this rusty red appearance. Another colour we'll keep an eye out for is a green colour. And this is because green rocks tend to be associated with essentially with wet environments. Most commonly marine environments, so saltwater environments. So if we see a rock that has a slightly green colour to it, as a geologist, that's instantly going to make you think, right, there is a good chance that this rock formed in some kind of water-bearing environment, and the green colour would suggest that it is probably a marine environment, so a saltwater environment. The final colour we'll keep an eye out for is black. Now, black, and we're talking black, not dark grey here. Black is typically the result of high levels of organic material in your sediment. Now, most of the time when you have organic material, it will decompose, and so it will not become incorporated into the sediment because it will break down before the sediment has been liquefied. However, if you have a rock or a layer of sediment that's forming in an oxygen poor environment, the organic material will not decompose because there's no oxygen there. Instead, it will become incorporated into the sediment, and when that sediment gets liquefied or turned into a rock, that organic material will become part of the rock, and it will have the effect of darkening the colour of the rock. And so any rock that's quite organic rich will tend to have a black colour because of the presence of so much carbon. And so the colour of this particular rock is telling us something about the amount of oxygen available in the environment. So obviously if we see a dark coloured rock, that would typically suggest the amount of oxygen is going to be lower. And so then as a geologist you have to think to yourself, right, what are the possible environments in which I could have this occurring? And so the colour of the rock is most of the time not helpful, but under certain conditions it can be quite useful to geologists. So when it comes to clastic sedimentary rocks, of course, we've already discussed how the size of the class, the shape of the class, and the sorting of the class are useful to geologists, mostly because they give us a good indication of how long the sediment was transported for. So typically a well-sorted sediment consisting of well-rounded class that are towards the smaller end of the scale is commonly an indicator of a sediment that's been transported for a long period of time. In contrast, a sediment that contains lots of angular class, which is very poorly sorted and has a range of class sizes, is typically seen for sediments that have not been transported very far at all. We're also going to look at the thickness of the beds. Typically, the thicker the bed, the higher the rate of sediment accumulation. So when we see a sequence where we have big, thick beds of rock, this is going to suggest to us that the sediment was building up quite quickly. And that would obviously help to explain why the layer is so thick. In contrast, when we have environments where the accumulation of sediment is very, very slow, what we'll get are very, very thin layers. So we'll get laminations. Remember, any bed that's less than 1 centimetre in width is referred to as a lamination. And so as a geologist, we will look at the bed thickness because it will give us some kind of idea about, how active the environment was, especially if it's towards the extreme ends of the scale. If we have very big, thick layers of rock, or we have very thin layers of rock. In the middle, where you kind of have medium thickness, that's not really going to help us too much. But if you're towards the end of the spectrum, well, then that's going to help you to gauge the environment. And then once again, as a geologist, you're going to think to yourself, right, what environments would I find very slow rates of sedimentation, or what environments would I expect to find very high rates of sedimentation? So it's going to help you to refine your model when you're trying to work out how each layer of rock formed. So the next thing we're going to look for is the type of bedding. So are we going to see normally bedded rocks, or are we going to see graded rocks? Are we going to see gradational contacts or sharp contacts? So we've already discussed this. So typically, if you have a situation where you have a change in the environment, that's going to lead to a nice sharp contact, and the layers of rock will typically be uniform because they are forming in just one environment. So they have a constant set of conditions. In contrast, when you have gradational boundaries and gradational layers of rock, that's telling us that the conditions in the environment are changing. So if we start to see things like gradational boundaries and gradational beds, that's giving us some indication about the environment. And once again, as a geologist, we're going to think to ourselves, right, what are the likely environments in which I would see this change in the amount of energy in the system? So then we're going to look for certain types of sedimentary structures. In this particular instance, we've gone for mud cracks. So a mud crack is simply caused when muddy sediment, which is wet, gets exposed to the atmosphere and it dries in the sun. So as the layer of mud dries out, the top of the layer of the mud will essentially begin to crisp up, and as it dries out, it contracts and it cracks. And it produces these things which we can see as mud cracks, and these can be preserved in the rock. There are also, of course, other sedimentary structures that we'll keep an eye out for, things like cross beds and ripple marks. And so these are all giving us some indication of how the sediment was forming. They're giving us indications about how the environment in which that sediment was being deposited would operate. And of course, the final thing we'll keep an eye out for are fossils, because fossils are extremely helpful when analysing sedimentary rocks. They tell us, are we on land, are we in fresh water, are we in salt water? If we're in certain environments, let's say the marine environment, are we in deep water or shallow water? Was the water warm? Was the water cold? And they also allow us to date the rocks as well, because we know the position of many fossils in geologic time, and so when we see that particular fossil in our rock, we can use it to date that rock. So there's lots of evidence that geologists will look for when analysing rocks to try and work out how they formed. So the next thing we're going to think about is we also need to analyse indications of current direction. So we're going to work out, which direction was the flow of water or ice or wind going. So we've already discussed crossbeds. So here you can see we have a sequence of sandstones, and the crossbeds are quite clear. So if we look at this bed right here, you can see we have this approximately triangular shape. So the bottom of the layer is coming through here like so, and the top of the layer is coming up here like so. And you can see we have these crossbeds that are dipping down towards the bottom left, and so we can see them there and there. So that's the dip of the crossbeds for this particular layer. Now we've already gone and discussed how when we're talking about crossbeds, we're talking about sediment being pushed up the stoss side of our crossbed, our dune, and then it slides down the lee side. So we know that these red lines here and the crossbeds represent the lee side of the dune. And so we can use the angle of these crossbeds to tell us which way the sediment was moving. And in this case, it was moving off to the left because the crossbeds are dipping down to the left. If they dip down to the right, that would mean the sediment was being transported to the right. Another feature we can look for when analysing sediments is called imbrication. And imbrication is simply the leaning of rocks on top of each other. Think of a row of dominoes that's been pushed over. Think how they'll lean on the previous domino. So what we have is a situation like this. So if you imagine that these 5 rocks are sitting in the bottom of our river, and the water in our river is flowing from right to left. Well, you will notice that these rocks are obviously going to be pushed by the water. So what's going to happen is the force of the water is going to push this yellow rock, so it starts to lean this way. The blue rock is going to be flipped up. The pink rock is going to be pushed to the left, and the orange rock is also going to be flipped up by the force of the water. And so what this means is the rocks are going to start to lie on top of each other, like so. And this is imbrication. So the imbrication is showing us the direction of flow. In that case, it would be going this way. So if we look in this picture here, can we see any signs of imbrication? The answer is yes, we can see them right there. So you can see how this rock is leaning on this rock, and this rock is leaning on this rock. So what we have is a situation just like this. So if you look at this yellow rock here, you can see it's dipping like so, and we can see the same orientation on this rock here. And so this is telling us that when these clasts were being orientated, the flow was coming from down here, the bottom right, and it was going towards the top left. The final feature we'll look for are ripple marks. And if you remember, ripples come in two varieties, asymmetrical and symmetrical. So asymmetrical ripples are caused by unidirectional flow. So that's the flow going in just one direction. So the classic example of that would be a river. A river only flows one way, and so that means the sediment is only being moved one way. And this will produce asymmetrical ripples. Also in environments that are exposed to the wind, that will also produce asymmetrical ripples. So if we look at our dune here, we can see that it's covered in ripples, and these ripples in this instance are very likely to be asymmetrical ripples. Now, just like a crossbed, we can use the asymmetrical ripples to work out which way the sediment is being transported. Now, the other type of ripple, which is a symmetrical ripple, that essentially has two sides to the ripple which are of equal length and occur at equal angles. And this shows us that we have bidirectional flow. So we have two currents going in opposite directions. And these types of ripples are most commonly associated with waves, because of course the wave goes up the beach and then it comes back down the beach. So that's our flow in two directions, one way up, the other way down. And so this is going to create a symmetrical ripple. Now these ripples aren't going to be quite as useful in terms of gauging the direction of flow, but they are going to be helpful in us analysing what the environment is, because symmetrical ripples are only really associated with beach environments that are being actively reworked by waves. Alright, thank you for watching everybody, and have a good day.